Hi everyone, this is Mrs. GA, and today we're going to be defining and evaluating logarithms. Alright, so I have a quick warm-up for you guys. So here you're asked to solve the following equation as much as you can. Once you get to a point where you're not sure what to do, just go ahead and stop. It will tie into the lesson. Alright, so here we are solving, this is what we call an exponential equation because the variable is in the exponent. So I think that you guys can probably use patterns based on previous equations we solved and say, okay, we should probably try to isolate this 7 to the power of x. So I can add 7 to both sides. I can multiply by 3, divide by 5. But from here, this is really where we get stuck. I mean, yeah, you could kind of guess and check. You could try plugging in different things. We know that x is going to be somewhere between 1 and 2 because 7 to the power of 1 is 7 and 7 squared is 49. So it's going to be some decimal. So rather than guessing and checking, we're going to learn a new operation to help us solve these types of problems. So that brings us to the definition of a logarithm. So what do you do if you're trying to solve for an exponent or if your variable is in the exponent? You can use a logarithm because logarithms define exponents. So if something is in exponential form, it looks something maybe like this, b to the power of x equals a. We can rewrite this in what's called logarithmic form. So you have your logarithm. The base of your logarithm is going to be the base of your exponential term, so base b. And then it's log base b of a. Notice a is what your exponential term was equal to, and then equals x. So notice that the logarithm is equal to the exponent because logarithms define exponents. So anytime you're trying to solve for something that is in your exponent, we can use a logarithmic form because, again, I can't say this enough today, logarithms define exponents. They're equal to the exponent. A few things about logarithms, though. The base must be greater than 0. So you'll never see a base of 0, and you will never see a negative base. And also, the base cannot equal 1. So the base can be a fraction. It can be something between 0 and 1. It can be anything larger than 1, but it cannot be 0, it cannot be negative, and it cannot be 1. There are a couple types of kind of special logarithms. The first is called a common log. So a common log is when you have a base 10 logarithm. When you write it, we would just write it as log of x. You don't actually write the base 10, but it's important that you know whenever you don't see a base and it's written like this, that it is implied that it's a common log, which is base 10. The second type of special logarithm is called a natural log, which is simply a base e logarithm. So you wouldn't actually write it as log base e of x. You actually write it like this. It looks like ln. We should read this as natural log of x. Please don't actually read it as ln of x. So still say the words natural log of x, but it's implied that this is just a base e logarithm. So it's important to know by looking at this what the base is. So those are the two types. Everything else, you will see the base of the logarithm written. Okay, so first thing we're going to do is we're going to practice rewriting from exponential to logarithmic form and vice versa. So here I have exponential form. So remember the base of my exponential term becomes the base of my logarithm. I know that logarithms define exponents, so it should be equal to 3, which means that the 64 must go here. Working backwards, I see that the base of my logarithm is 5, so that's the base of my exponential term. Logarithms define exponents, so I know that my exponent should be negative 2, and the result should be 1 over 25, which is what we see here. Here, again, the base of our logarithm is 2/3. I see that the exponent is p, so that must be what my logarithm is equal to, and it must be of q. So we read this log base 2/3 of q equals p. And let's do this one, log base 1/2 of m equals n. So my base is 1/2. My exponent is n because logarithms define exponents, and it will be equal to m. All right, go ahead and pause the video and give this one a try on your own. All right, check here for this first one. You should have log base 3 of 243 equals 5. Here you should have 4 to the power of negative 3 equals 1 over 64. Here log base 3 over 4 of w equals t. Again, logarithms define your exponent. And here you should have 1/5 to the power of y equals v. So now looking back at the warm-up, we got to this point in the warm-up, and now knowing what we know, we could actually take this and rewrite it in logarithmic form because, again, logarithms define exponents. So I'd have log base 7 of 9 equals x. And this actually would be an exact answer for x. So from now, we are able to actually solve for x. And I'll show you a little later on in the lesson how we could get a decimal approximation for something like this in our calculator. But again, now once you have something like this, we can simply rewrite it in logarithmic form to help us solve for anything that's in an exponent. Okay, so now we're going to practice evaluating logarithms. So every logarithm will have a value, and that value will depend on the base and the result here, what you're taking the log of. So here our function is the log of x, and we're asked to find these following ones. So the first thing we're asked to find is f of 1,000, which means the common log of 1,000. Remember, when you see something like this, a common log, it's implied that the base is 10. We don't write it, but I'll write it in here just to help us solve this problem. So remember, logarithms define exponents. They're equal to the value of the exponent. So I'm in my head essentially saying 10 to what power is 1,000? Or if I were to rewrite this, I'll say like 10 to what power, I'll do question mark, equals 1,000. So I'm wondering if this is my base, this is my result. Oh, my exponent must be 3 because 10 cubed is 1,000. Now let's look at the next one. They want us to find the common log of 0.01. For this one, it might actually be easier for us to rewrite this as a fraction. 0.01 is just 1/100th. So again, I'm asking myself, 10 to what power equals 1 over 100? Well, I know if I'm going from something like 10 to something of 1 over, that my exponent must be negative because a negative exponent causes that reciprocal action. And I know that 10 squared is 100. So my exponent must be negative 2. The negative flips it, and then the 2 squares it, so from 10 to 100. And last, I have f of root 10. So we're finding the common log of root 10. This one, it might be easier for us to look at it like this. We know that the square root of 10 is 10 to the power of 1/2. So we're kind of saying 10, the base of our common log, 10 to what power equals 10 to the power of 1/2? Well, it must be 1/2. So our exponent is 1/2. So remember, anytime you see a radical, or if you notice that the value is the square root of your base or the cube root of your base, your exponent must be it should be a rational exponent, so it will be a fraction. Okay, let's try another one together. Here I have a log with a base of 1/2 as our function. So first they would like us to find f of 4, so log base 1/2 of 4. So again, I'm essentially saying 1/2 to what power equals 4. So first I see that my exponent will be negative because I go from 1 over 2 to suddenly the reciprocal of that. So I know the exponent must be negative, and I know that 2 squared is 4. So the negative flips it, and the square turns it from 2 to 4. All right, let's find now f of 1 over 32. So we're finding the log base 1/2 of 1/32. So I'm saying 1/2 to what power equals 1 over 32. So I know that 2 to the power of 5 is 32. So the exponent must be 5. And notice it's 1 over 2 and 1 over 32, so the exponent does not need to be negative here. Okay, for this last one, log base 1/2 of 2 root 2. it might be easier for us to rewrite this with a rational exponent using our properties that we learned before. So 2 times 2 to the power of 1/2. And we can actually multiply those terms because they have the same base. So we add up the exponents. So it's 2 to the power of 3/2 because 1 plus 1/2 is 3/2. Add up the exponents. So I'm saying 1/2 to what power? 1/2 to what power is equal to 2 to the power of 3 over 2. So I know for the 2, the 1/2 to turn into a 2, it should be a negative exponent. And then if I put the negative exponent on this side, it flips it to a 2. So then we still have that exponent of 3 over 2. So the answer is just negative 3 over 2. Again, the negative will turn the 1/2 into a 2, but then I need to raise it to the power of 3 over 2 to match this exponent. So again, sometimes you're going to want to try to rewrite what's within your logarithm because it might make it a little bit easier for you to simplify, especially when you're not using a calculator and you want an exact answer. All right, so I have one for you to try on your own, so please pause the video and give it a shot. All right, so go ahead and check your work here. And again, for part C, it probably will be much easier if you think of square root of 7 as 7 to the power of 1/2. Okay, so now let's talk about how to get decimal approximations for logarithms that don't simplify out to be like nice numbers or ones where you can't find an exact value. So your scientific calculator can only compute common logs and natural logs. But what if you have maybe like a base 7 logarithm that you want a decimal approximation for? How do you do that? So for something like that, we're going to use the change of base formula. So really this formula is only used to help us compute a different base logarithm to get a decimal approximation. So if you have log base b of a, the change of base formula allows you to rewrite any logarithm with any base logarithm that you want. We would really only use common log or natural log because, again, we're just trying to plug this into our calculator. And just so you see on our calculator here, this is the common log button and here's the natural log button. So you can rewrite any logarithm to look like this. So it's the common log of a over the common log of b. So notice this term goes on the top and the base goes on the bottom. Or you could do the natural log of a over natural log of b. And this is something that you can plug into your calculator to get a decimal approximation. And whether you use common log or natural log, you'll get the same result. So again, we really just use the change of base formula to take a logarithm that our scientific calculator can't compute and write it in a way that it can, so we can get a decimal approximation when necessary. So let's use our scientific calculator to get a decimal approximation for these expressions. So natural log of 5, you can actually just plug that straight into your calculator. Again, that natural log button is there, and it says round our answer to nearest hundred. So make sure you can plug this into your calculator and get approximately 1.61. So make sure you are able to do this in your calculator. Here we have a common log, so again, your calculator can do that. So just hit that common log button of 457, and let's round it to the nearest hundred. So 2.66 should be what you get if you round properly. So again, make sure you know where these two buttons are. And then for this last one, again, your scientific calculator cannot do any and all bases of logarithms. It can only do common logs and natural logs. So we're going to need to rewrite this using our change of base formula. So you can either rewrite it as the common log of 95 over the common log of 8, or you could do natural log of 95 over the natural log of 8. And either way, you should get the same approximation. So let's do common log of 95 divided by common log of 8. You should get approximately 2.19. And if you do that same thing with the natural log, you should get that same exact decimal approximation as your answer, 2.19. So again, whether you're rewriting it to have a common log or a natural log, it's up to you. The only purpose really of this change of base formula that we will be using it for is to take something like this and to get a decimal approximation with our calculator. All right, so that is all for today's lesson. Thank you so much for watching.